Students, welcome to another session of All Force e-learning program. Right now, in this session, we will derive a formula for the electric field due to a conducting solid sphere, charged conducting sphere. Electric field due to a charged conducting sphere. Conducting charged sphere. We'll deduce a formula for the electric field due to a conducting sphere there, right? So before going to this, let's have a review. What are all the things that are required to deduce its relation, right? So I was telling you, charge, everybody, whenever charge is given, it produces a field around it. The space around the charge where the effect of the charge can be felt, experienced, is field. You know, every charge produces lines of force around it. So these lines of force are spread within the field, is it? So field has strength, electric field intensity. The strength of the field is electric field intensity. In this episode, we are going to deduce the electric field intensity for the conducting sphere, charged conducting sphere. Well, we know electric field intensity, it is the force experienced per unit charge, F by Q, electric field intensity. Then, when the charge produces lines of force, the measure of number of lines of force, count the number of lines of force passing through a particular space, whatever space of concern, that particular space, the count, the number is called electric flux. The number of lines of force is electric flux. Well, next, electric flux density. Electric flux density or electric field intensity, electric field strength, all the three mean the same. So electric flux density or electric field intensity E is electric flux density E, it is phi by A. So cross multiplying flux phi is E dot A, it is E dot A. So E flux is EA cos theta. For uniform field, we take flux phi is equal to EA cos theta. If it is a non-uniform field, so for uniform field, flux is E dot A, EA cos theta, right? Or flux is E dot A. For non-uniform field, the small flux through a small area element. Consider a small area element of this area, the nail, for example, right? Through that area, the small flux d phi is E ds, E dot ds. Then, when you enclose the total surface, for a total surface, when I take such area elements, covering all the total enclosed surface, then the total flux through the enclosure is integral d phi. It is the surface integral of surface integral. So it is integral surface integral E dot ds by definition of the electric flux. Next, Gauss Law, a very important tool, an alternative for Coulomb's law. It's almost like Coulomb's law, but Coulomb's law has a restriction that it is applicable only for point charges. But Gauss Law is applicable for any charge distribution. Well, it is easy for uniform charge distribution. So, according to Gauss Law, the total flux through a Gaussian surface, you have to enclose the Gaussian surface, enclose the charge, whatever that is given with a Gaussian surface. The flux through the Gaussian surface is 1 by epsilon naught times the charge that is enclosed inside the Gaussian surface. It is 1 by epsilon naught times this. So, equating both, integral E dot ds, the total flux, surface integral of the total flux through the Gaussian surface, E dot ds is Q by epsilon naught, the mathematical form of Gauss law. And this is the basic law which we will be using to derive this, right? Yes. Now coming to the conducting charged sphere here, conducting sphere. Now consider a charged conducting sphere. A charged conducting sphere of radius r. It's a solid sphere. I am giving charge. Now, whenever charge is given to a conductor, now what happens actually? How charging charging of a conductor take place. For example, suppose I am charging this by conduction method. So I was explaining you in the earlier chapter, in the earlier episode, when a charged conducting body is to be charged, right? I get a charged body. There is a already existing charged body with some charge in it, charge existing on it, and a conducting sphere. So I put in contact. So when you put a charged body in contact to a conductor, then charge flows from this body to the sphere there. Suppose, look, imagine there is a glass rod. This is a glass rod. Charge being given to it. Already charge is existing on the glass rod. I have produced charge on the glass rod by rubbing it with a silk cloth. Then, so when a charged glass rod like this with a handle, let us say, now it is put in contact with a sphere, a conducting sphere. Then what happens when both are put in contact? Then this positive charge. So this is a conductor. You know what is a conductor? A conductor is a substance which possesses abundant number of free electrons at this room temperature. You know, electrically all the substances are classified into three categories: conductors, semiconductors, and insulators. Conductors are those substances which possess abundant number of free electrons readily available at room temperature. Right? Free electrons. The electrons come out of the outermost shell and they exist freely coming out of the atoms there. So there are abundant number of free electrons already existing in it. Free with no boundary, no being bounded to the atom there. They are free, existing free. Well, insulators, the number of electrons are very less, negligible. That doesn't come into count there. Okay. So already there are number of free electrons existing. We know, I was telling you, charging takes place by transfer of electrons. So when I put this glass rod into this conductor, already existing electrons, now those electrons migrate from the conductor to this. So one electron, when it migrates into this one, it will neutralize one of the positive charge. So when electron goes away from it, from out of the conductor, then the conductor gets positive charge. Then this gets a positive charge. Let us say it has got a positive charge. It gets a positive charge plus. Now, when the second electron is added to, electron migrates from the conductor to this, it will neutralize the positive charge on the glass rod. Now, a positive charge is obtained on it. Now, when the positive charge is obtained on it, the positive charge obtained on it. So, this second electron, when second electron migrates the charge. Third one, fourth. So the charge that is given to a conductor is distributed uniformly whenever you charge by conduction, right? Conductors are charged by conduction usually, right? When you charge by conduction like this, then the electrons transfer from the conductor to this, then the electrons transferring from the conductor into it neutralize the positive charge, and the positive charge appears here. Now charge is conserved. Charge will be conserved. This loses positive charge, this gains negative charge. This is losing electrons, this is gaining electrons. Electrons are transferred from here to here, positive charge is transferred from here to here, right? Total net charge is again constant. So positive charge, it gets positive charge. So when you are charging a conductor, then the charge on a conductor is distributed uniformly. The reason for it is, when you give a charge, wherever you give charge, now charge reaches the surface. Charge migrates to the surface. It reaches the outermost point of the outermost boundary of that conductor. Take any conductor. When you give charge to it, it takes the outermost this thing. Second one, it takes this. Third here, fourth here. So the charge is distributed uniformly, such that equilibrium is maintained, such that the equilibrium of charges, because in a conductor the charges are repelled. The electron, the charge that is being given, they experience force. They move away to the outermost surfaces like this. They move out to the outermost surface. They stretch on like this. When you give charge to a conductor, no charge exists inside the conductor. So this is an important point to remember. Any conductor, when you give charge, when it is charged, charge exists only on the outer surface. Based on this, an experiment, practical experiment was also conducted, right? A charged spherical shell was considered. A person is made to sit inside the charged shell, and the shell was given charge, but the person inside the shell experienced no electric shock. Right, that is a practical proof to say that the charge exists only on the outer surface of a conductor. This is only for a conductor, please. For a conductor, whenever charge is given, charge exists only on the surface. Even if you produce charge inside, even if there is charge being created inside, then that charge migrates to the surface. Right, due to some process, charge appearing inside, that will move to the surface. So charge exists only on the outer surface of a conductor. So for a charged conductor, conducting charged sphere, whenever charge is given to it, charge exists on the outer surface. If the first charge appears like this, charge is quantized. Charge is given in packets, in integral multiple of electrons. When the first electron migrates, charge appears here. When the second electron, now the charge appears in the extremest point like this. When the third, then these three are arranged in the form of an equilateral triangle actually. Right? These three appears like this. When fourth charge is given, then these four charges appear as four charges of a square like this. Fifth, they form a pentagon. Sixth, an hexagon. So they form regular this thing. So as the charging take place, they take up the extremest points of the surface. No charge will exist. Charges tend to move apart. They try to move apart away from one another. So when they try to move away, they reach the extremest points. So on the conductor, they reach the outer boundary. They cannot go out of the conducting sphere, conducting surface. So all the charges reach the extremities of the surface. Take any charge body. When charge is given, they reach on to the extremities. Right? This charge, even if the charge appears here, now that goes to the extreme like this. So charge is led to the outermost surface. They reside on the extremities boundary of the conductor. Now this is an important point to remember. Whenever charge is given to a conductor, charge reaches the extremities, right, stays on the boundary of the conductor. So a charge q, let a charge q is given to the sphere of radius r. So for a conducting sphere, charged conducting sphere, the charge exists only on the outer surface. There is no charge inside the conductor. Now this is an important point to remember. Okay, now for this conducting sphere, we have to find the electric field intensity. Now this is similar to a spherical shell. In the previous episode, we have taken, right, the charged spherical shell for which the charge is existing only on the outer surface. Even if it is a bad conductor also, insulating hollow sphere, charge exists only on the outer surface. There is no possibility of charge existing inside because it was hollow. Charge resides on matter. There need to be matter existing for the charge to reside on it. When there is no matter inside hollow, there is no charge inside. So even if it is a non-conducting sphere, right, for a non-conducting sphere, charge given, charge resides on the surface. So now our conducting solid sphere, charged conducting solid sphere is similar to a hollow spherical shell charged. When charge is given to a hollow spherical shell, this behaves as the hollow spherical shell. Well, similarly, let us derive the formula for the electric field intensity due to this one. Again, we have to derive the formula for the electric field at three different points. Let's consider an outside point P. Outside point P. So the electric field due to the charged sphere at an outside point. Now for this, there are some steps. First, we have to imagine a suitable Gaussian surface. Now let me give you clarity regarding how do you imagine a suitable Gaussian surface for any charge distribution. Now, suppose, let me give you a table like thing. Let me show by a table. So this is the charge distribution, the various charge distributions. This is the charge distribution. The suitable Gaussian surface, what Gaussian surface you can imagine, the suitable Gaussian surface, and the direction of the electric field for that, the direction of the electric field for that charge distribution. Right now, so we come across various types of charge distribution. The first one, if it is a point charge, if it is a point charge, then the suitable Gaussian surface to be imagined for a point charge is spherical Gaussian surface. You have to imagine a spherical Gaussian surface. Then the direction of the electric field is radially outward. It is radially outward. Or for positive charge it is radially outward, negative charge it is radially inward. So the direction is radial along the radius there. Is it? So you please remember this table. According to this you have to imagine the Gaussian surface suitable for various charge distributions. So for a point charge you have to imagine a spherical Gaussian surface. The direction of the electric field is radial. Why spherical Gaussian surface for a point charge? Because when you take the distance, all the points are at same distance. At all the points on the Gaussian surface, the field will be same, and it will be radially outward from the surface. Second one, suppose if it is a thin wire, cylindrical charge. It is a cylindrical charge distribution. Then for a wire, we have derived for a wire. So then the suitable Gaussian surface is cylindrical Gaussian surface around that wire, charged wire, for example, thin linear charge. This is cylindrical charge, or you can take a linear charge. If it is a linear charge or charge spread on a wire, charge spread on a cylinder, charge on a glass rod, then the Gaussian surface is cylindrical Gaussian surface. So for a charged wire like this, you have to imagine a cylinder around it which is equidistant, suitable for it, and it is equidistant. The electric field at all the points will be equal, and even the direction is also radially outward. It's again radial. The direction is radial. At all the points on the surface, the electric field will be normally outward for a positive charge like this. So for a linear charge, linear line of charge, charged rod, cylindrical charge, for all such things, charged wire, is it? For all such things, you have to imagine a cylindrical Gaussian surface where the direction is radially outward. Third one, suppose if it is a plain charged sheet. It's a plane of charge, a charged sheet, infinite plane of charge, right? Then the direction of the Gaussian surface should be parallel to the surface, symmetrically bounded on either sides, parallel to the plane sheet, parallel to the plane, such that electric field is normal to the surface, normally outward to the plane of the sheet, right? Suppose if I consider a plane sheet like this, then if it for a plane sheet, then parallel to this sheet you have to imagine a Gaussian surface, enclosed Gaussian surface in front, and it will be symmetrically behind also. So the Gaussian surface should be parallel to it like this, enclosing. Well, you can enclose in the form of a cylinder or in the form of a cuboid. This is parallel like this, and even a similar thing existing on the other side. This sheet should go through the Gaussian surface symmetrically on either sides. Is it? A plane sheet here, plane parallel to it, and a plane parallel to it, right? Both connecting, enclose the Gaussian surface. And field at any point on that, field on this plane surface is outward normal. The direction of the plane will be outward normal like this. So that way you should imagine the Gaussian surface. And the fourth one is spherical charge distribution. First, if the charge distribution is a discrete charge, a point charge, then the Gaussian surface is spherical and the direction is radially outward for positive. If the charge distribution is linear, So charge is distributed linearly like this in the form of a charged wire or a charged cylinder. Then you have to imagine a cylindrical charge Gaussian surface. Again, the direction is also radially outward from that line of charge. Third, if the charge is on a plane sheet, on a plane charged sheet, the charge distribution is on a sheet, on a plane, then you have to imagine a surface parallel to the plane. Gaussian surface parallel to the plane, enclose it on either side symmetrical to the plane sheet. The direction of the electric field is normal to the plane, whatever you imagine. Plane normally away from the plane, whatever you imagine. If it is a spherical charge distribution, again the Gaussian surface is also spherical and the direction is radially outward. The direction of the electric field is radial outward. So you please make a note of these things, and this is very important to remember. For various charge distribution, point charge, linear charge, plane charge spread on a plane, charged plane sheet, right? Then spherical charge distribution. For these respective charge distributions, the respective Gaussian surfaces, right? For point charge it is spherical, for spherical it is also spherical there because it should be symmetrical. Then for linear charge it is cylindrical Gaussian surface. So whenever you come across a linear charge, imagine there should be a cylindrical Gaussian surface equidistant from it. And fourth, the plane sheet. If the charge is spread on a plane, then for a plane, so for a plane like this, imagine a Gaussian surface parallel to it, parallel to the plane sheet like this. Right, imagine a Gaussian surface for a plane, imagine a Gaussian surface parallel to it, right? Then enclose it by, if I take a circular plane for example, then enclose it by a cylinder and imagine it equally on the other side also. Or if it is a square plane, if I imagine a square, then enclose it by a cuboid. So, imagine the same thing on the other side also. So for a plane sheet, charged plane, then the plane should be, Gaussian surface should be a plane parallel to it, enclosed on either sides. Well, the direction will be normally outward to that plane. And for a spherical charge distribution, Gaussian surface is spherical, the direction of the electric field is radial. Very important to remember, right there. Now let us imagine, according to the nature of the charge, you please imagine the Gaussian surface and the direction. Based on that, you evaluate deduce the respective electric field for various charges. Now coming to our this thing, so it is a spherical charge. So for a spherical charge, the Gaussian surface should be spherical. So imagine a spherical Gaussian surface around this spherical charge, concentric to this sphere, conducting charged sphere. So the Gaussian surface is a spherical Gaussian surface at point P. Now the direction of the electric field is radially outward. So the direction of the electric field at any point is radially outward. For positive charge it is outward. Had it been a negative charge, then it would have been inward. But it is radial. It is radial. So the electric field is radially outward like this. Imagine a small area element, very small area element of this area. The area element is ds. We know for any area element the direction is outward normal. I was telling you the direction of the area element is always normally outward ds. The small flux through this area element, it is E dot ds. But the direction of the electric field and the area element both are same. So d phi is equal to E ds cos 0. So d phi is E into ds. Well, if I consider such area elements on the surface, Gaussian surface, all such area elements on the Gaussian surface, like, let me give an example. Take a football. You know, on a football you find some patches, black and white patches. So the area element what we consider is equivalent to one of the patch, one certain patch, right? Then if I integrate on that patch, the electric field is small flux d phi E ds. If I consider all such patches together and integrate for all the things, find the total flux due to all such patches on the sphere, then the total flux phi is integral d phi. That is, total flux is equal to integral E ds. But you know, the total flux coming out of that sphere there, when I was considering those circular patches, the total flux through all those patches, it is E ds. But you know, for all the points, the electric field here is a constant. So I was telling you, whenever you imagine a Gaussian surface, first thing, it should be symmetrical to the charge distribution. Second thing, it should pass to the point where the electric field is to be found. I want to find the electric field at point P, so the Gaussian surface is passing through the point P. Third, the electric field should be same at all the points on the Gaussian surface. It should be equal. So the Gaussian surface is equidistant from the charge. So the electric field is a constant, and the direction is either normal or tangential. So the direction is normally away like this. So we have followed all the restrictions that are required to imagine the Gaussian surface. So at all the points, the electric field is same. So this is a constant. So the total flux is E integral ds. Now what is integral ds? The area of all the elements what I imagine on the Gaussian surface. So I was telling you, the patches what we have imagined on the ball there. So the area of all the patches together is the total area of the sphere. So the total area of the sphere, so the total flux is equal to, the total flux is E into integral ds. That is 4 pi, the radius of the Gaussian surface. I have imagined the Gaussian surface at distance r, so it is 4 pi r square. Point P is at a distance r, so the area of the Gaussian surface is 4 pi r square total flux. Well, so first we have used this. Then applying Gauss law, we know according to Gauss law, the total flux is equal to charge enclosed inside by epsilon naught. This is the Gaussian surface we have imagined, and inside this Gaussian surface the charge is the charged sphere. It's nothing but Q by epsilon naught, that is 2. So equating 1 and 2, equating these two, I get, so E into 4 pi r square is equal to capital Q by epsilon naught. So E is getting this 1 by 4 pi epsilon naught Q by r square. Epsilon naught Q by r square. This is the electric field due to a charged conducting sphere. Is it conducting charge sphere, charge uniformly on the outer surface? This is again similar to, we have derived the same thing in the earlier session for a hollow charged sphere, any nature, whether it is non-conducting or conducting. For any hollow sphere also you got the same answer. Even for the point charge also it is the same there, right? Point charge. So according to Shell, there are two theorems. Shell theorem. So electric field due to this sphere is same as the electric field due to point charge, right? So this is the electric field at the outside point. Suppose if I imagine a point on the surface, when I imagine a point on the surface, then small r is capital R. When you imagine so for small r is equal to capital R, point on the surface, then the electric field on the surface is 1 by 4 pi epsilon naught capital Q by r square. This is the electric field on the surface. Now if I imagine a point inside the sphere there, for any, this is the charged sphere, this is the charged conducting sphere. So I was telling you, for a charged sphere, charge exists only on the surface. So if this is the center, if I imagine a point P inside at a distance small r less than capital R, where capital R is the actual radius of the sphere, r less than r. This is the electric field for r greater than r. This is the electric field for r equal to r. If I imagine a point inside, then the distance of the point is r less than r. Then how about the field here? Now imagine a Gaussian surface again inside, right? According to the same derivation, the electric field, the total flux by definition is E into 4 pi r square, right? According to Gauss law, it is charge enclosed inside the Gaussian surface by epsilon naught, charge inside by epsilon naught. But for a conducting charged sphere, there is no charge inside. Any charge produced will reach the outer boundary. All the charges exist only on the outer boundary of a conductor. So charge inside is 0. So the electric field at inside point is equal to 0. The electric field at the inside point is equal to 0. So for a conducting charged sphere, it is same as for a spherical shell. Charged spherical shell, we got the same electric field at the outside point, electric field on the surface, electric field at inside point, right? Same formulas as the for hollow charged sphere, whether it is conducting or non-conducting. Hollow sphere and conducting charged sphere both have the same electric field. Is it? Both will have the same electric field. So this behaves as a hollow charged sphere there. You can imagine, you can remember it as a hollow charged sphere. So hollow charged sphere, any sphere, solid or conducting, any nature, right? So hollow charged sphere, whether it is conducting or non-conducting, and a charged conducting solid sphere, both behave the same. Same formulas will be getting. Right? Thank you.